All right. I'm John Baker. And as was introduced at the end of the last session, the end of the whole program, we're gonna look to that future a little bit. And so, and since it's also the end and we're looking to the future, I am not going to really attempt to teach you how to do anything here. I'm hopefully going to be showing you a lot of pictures. You can relax. You can enjoy nice pictures. And you can hear about where we're going as we move into the future of gravitational waves, the hopeful future of gravitational waves. So to get kind of an overview of the landscape of the gravitational wave future, we can look at plots like this, and you've seen a few plots, I think, of this nature already in the program, but on the bottom axis is the frequency of the observed gravitational waves, or the potentially observed gravitational waves. And on the top, the left axis is the gravitational wave strain, right? So louder gravitational wave signals are higher up. And so on the far right, the pointer, whoops, going too far, jumping ahead. On the far right, you can see detectors that are the ground-based observatories. One of which we have is of the one of the which that is on there is one of the ones that we are observing with now. And the other two are future proposals for ground-based observatories. But we can't so we can improve. You know, if you're expanding a field of astronomy, right? You have a couple directions you can go. You can make your telescope or your observatory more sensitive, or you can make your telescope work differently and observe in a different band. In electromagnetic observatories, right, we started looking at the sky optically, right? And then we moved into eventually observing in the infrared and in X-rays and in gamma rays and in radio waves. So we're observing the sky across the entire electromagnetic spectrum and learning a lot as we do so. So we can do the same kind of thing with gravitational waves, right? So we are starting to make observations in the nanohertz band on the far left side here, which is the domain of gravitational waves that have periods that are longer than years, like, which is in terms of the frequency nanohertz regime, orders of magnitude within nanohertz, right? And then there's the ground-based observatories. They're making observations that are in the tens to hundreds of hertz is their most sensitive region, right? For the middle region, which I'm calling the millihertz band, is another one which we are going to be moving into making observations in about 10 years from now, right? So, and so I'll spend a fair amount of the talk talking like that because that's what I actually know something about. I work on LISA. So if you're going to move into new bands, then you're going to be also observing new types of phenomena, right? So when you open a new site, look with a different type of telescope at the universe, you can look at the same systems, sometimes the same systems in a new way, and you can see other systems, other types of things that you couldn't see at all before, right? So same kind of thing is true in gravitational waves, right? So as we improve in sensitivity, as we go to broader bands, we're going to be seeing a lot more different kinds of sources. So there's a number shown on here. I'm not going to cover them all now, but we'll talk about some of those in a little more detail later. Oh, okay. All right, well, this is confusing. Okay, to get a basic understanding of, what changes when we look at a different frequency band, there's some fundamental physics of what we kind of expect to observe when we go from the higher frequency end of gravitational waves to the lower frequency end, right? So if you're observing a system of the same mass, when you go to a lower frequency, you're observing it before it chirped up. And so the frequency is lower. The system is actually if it's a binary, the pair of objects that are orbiting each other are going to be farther apart, and the gravity is going to be weaker. So you're observing it actually in a domain of weaker gravity, and in particular, gravity will be less dominant. So there's more opportunity that other things that aren't just gravity can be having an impact. So you can have more chance of observing the effects of the environment to the system, of observing the details of the structures that are involved, that are not just gravity, right? Another thing, also because they spend a lot more time there, they're much more common. So you're going to be seeing larger numbers of them, which means that they'll happen faster. They'll be happen more frequently, or possibly they'll be persistent. If you don't fix the mass, then as you go to lower frequencies and you think I'm looking at the mergers of black holes, you're going to see the merger, instead of seeing mergers of black holes that are 30 solar masses, as you see with the ground-based observatories, you're going to see mergers of black holes that have masses of tens of thousands or hundreds of thousands or millions of times the mass of the sun. All right, I got to learn how to click at the right time. So, and then to make these different observatories, we have to take different approaches because we're looking at very, very different frequency bands. So these middle millihertz bands are 4 orders of magnitude lower in frequency. So it's a very different type of technology, but a very different approach that you have to take in order to observing the system. So roughly speaking, for gravitational wave interferometers, the size of the interferometer scales with the observation band. So for the ground-based observatories that we're using now, the observatories and to some degree the wavelengths of the signals are on the order of kilometers, right? For the millihertz band, the wavelengths and the size of the observatory is moving up to billion meter scale, right? And we don't have property on Earth of billion meter scale, so you have to go to space in order to be able to do this. And you want to go many orders of magnitude down, well, the solar system is not big enough. So those observatories are built out of observations from large numbers of pulsars in our neighborhood of the galaxy. I will say less about the pulsar timing observatories in the nanohertz band. I will say something about the millihertz band, future detectors planned, particularly LISA. And I will say something about futures for the so-called 3G observatories in the current band of the ground-based. All right. So for the space-based observatories, definitely the future gravitational wave instrument for which there is a strong commitment to actually building it is LISA. The European Space Agency is committing to do this. It is this light blue object here in this diagram, which includes a number of possible future space-based observatories. The idea is that you have 3 satellites that are orbiting each other in a triangle kind of configuration. They're the same distance roughly from the sun as the Earth is, but they're not right around the Earth. And they're not being held in a triangle shape. They're each on these elliptical orbits that are just balanced so that when one's going out, the next one is going in, so that they kind of always stay in an approximate triangle shape. It's kind of ingenious, actually. But and then there's lasers going between them and test masses. I'm not going to talk about the technology really, but and the scale of that is, the LISA's plan to be 2.5 billion meters between the spacecraft. And that gives you the sensitivity in the band of the millihertz band that we're interested in. It's not the only observatory being considered in this with a similar kind of technology and similar kind of range of observation frequencies. For a long time, there's also been a lot of interest in a project called the SIGO, which is a more aggressive project. It's more sensitive. It's a little bit higher frequency band. You can see there could be possibilities of having a number of different parts of it. I'm not going to talk much about that. It's a little bit farther from being realized than some of the other possibilities may. There's also 2 concepts being developed in China. One is called Taiji, which is very much like LISA. For the purposes of this talk, it's pretty similar in its concept. And then there's another one which is a little bit different because instead of having 3 separate spacecraft on these elliptical orbits, you have them orbiting around Earth. All right, so probably going slower than I should here, but I'm going to this is another version of the same kind of plot with the sensitivity curves. But now we've zoomed in on the sensitivity curve for LISA, and we'll talk specifically about some of the sources for LISA for a few minutes here. Here is one of the big categories of source for LISA is the massive black hole binaries. So instead of black hole binaries of 30 or 100 solar masses, we're talking about black hole binaries of 10 to the 5, 10 to the 6, 10 to the 8. But this plot here in the background, I'm going to stick with it for a while. It includes a number of different types of sources for LISA. So these massive black hole binaries are made from these massive black holes live at the centers of galaxies. And so as we look back over cosmic time, the galaxies have been evolving, the galaxies have been forming and merging together. And as they do, we believe that the black holes at their centers merge together over time as well. And so something about that process of the formation of galaxies, structure formation, development of the universe will also be traced in the mergers of these black holes. And then in the bottom part is a picture of merging black holes with some gases around. So bigger black holes have better opportunities for having gas present, which means we're hopeful that there's the possibility that there's electromagnetic counterparts to these, so we don't know how to look at them yet. Not guaranteed. All right, a little bit more on the massive black holes. If the figure on the left side here is showing you the sensitivity, the signal to noise ratio for massive black hole observations with LISA. So, for the ground-based observatories, we've been seeing signal to noise ratios of, a few tens is a typical signal to noise ratio there. For LISA, the signal to noise ratio here is on a log scale, which you see from the colors. For the sort of the middle band light blue, which you can see is a signal to noise ratio of more than 100. And you can see for the 10 to the 5, 10 to the 6 mass range, you have signal to noise ratios of more than 100 all the way out to redshift of 12 in this plot, which is possibly as early as these systems would exist. So you're seeing really, really clear observations of these in parts of the band, anywhere they likely to have formed in the history of the universe, which is kind of amazing. The right side here, the patches of yellow and blue are a couple of different models kind of predicting the populations of these mergers and where the sort of history of black hole mergers live in this space of and there are two different models depending on the formation process of the black holes. But so you can see that the sensitive part of LISA is also, a very interesting part when we're trying to understand how the black holes at the centers of the galaxy got there and what their binary populations are like. The stuff on the right side here, the stuff on the right side was electromagnetic observation. So as you can see there, what we've observed so far is actually kind of a different part of the population. Let me keep moving. All right. Another class of binaries for LISA, which is actually much more numerous, are the binaries that are in our galaxy. And they're not huge black holes. Now they're actually smaller objects. We think one of the main candidates for formation processes for the black holes we observe with LIGO is that you have these large stars that lived through their life, ran out of energy, collapsed to form black holes, and form these massive black holes. Or slightly smaller stars, still large, that collapse to form neutron stars. But if the black hole, so the original star isn't big enough, it won't form either of those. And a star like our sun isn't going to form a neutron star or black hole. When it runs out of fuel, it'll form a very tiny, compact white dwarf stellar remnant. The super tiny star that's not really burning anymore, but it's still hot, so you can see it sometimes. So there are many white dwarfs out there, and it's possible, the many scenarios for actually bringing the white dwarfs close enough together, the same processes, similar processes to those which allow the black holes to become close together and emit gravitational waves, and also bring white dwarfs close together from a binary stellar system. And so we think that there are millions of these types of binaries in our galaxy, and LISA is likely to be able to observe tens of thousands of them. So it's a large number of systems. And that's actually too many because in parts of the band, there'll be so many that we can't even really distinguish them from each other. And so we have a new kind of challenge, which is this big confusion of the many signals that we have. It also allows us, you see kind of in the bottom right corner here, out of the entire population, we can do things like actually make pictures of the galaxy in gravitational waves, which is a little bit more like a kind of the familiar space for observatory where we're making pictures. But we can learn something about where the white dwarf binaries are distributed in the galaxy, and we'll be able to observe many more white dwarf binary systems with gravitational waves than we have observed so far electromagnetically. One thing that's particularly exciting is little red blobs on this plot are binaries that we actually already know about. We can observe these things electromagnetically, and then we can go back and hopefully we'll find them in LISA's data as well. And so we call them verification binaries, but that's one of the really exciting things. They're a guaranteed multi-messenger source. All right, another very exciting new class of source for LISA is what we call extreme mass ratio in spirals. In this case, it's kind of putting the different pieces together. We have a massive black hole at the center of a galaxy, and then you have a small black hole that's only 30 times the mass of the sun, or 10 times the mass of the sun or something. And it falls into the massive black hole. And as it does so, it'll spend a long time orbiting in the strong gravity part of the larger black hole's environment. And so it can actually be strongly affected by general relativistic effects, and you can get complicated signals out, which carry a lot of interesting information about that environment. All right, one of the possibilities, now I'm just showing you here some plots. I mentioned there's some Chinese observatories too. Wow. And LISA is this blue curve. This is a cumulative signal to noise sort of set for observations. With the Chinese missions there, the other colors, the different this possible Chinese missions. There are different places you could put this Taiji mission. You could put it in the same place as LISA, or you could put it in a different place. You put it in the same place. The plot on the right shows that you don't really get much benefit in the sky localization of the sources, but you get many orders of magnitude benefit if the green and red curves are far to the left. Much better sky localization if you can have two instruments operating at the same time. So that's something we should all hope for. Okay, so now we move on to the ground-based future. The so-called 3G projects, third generation. There's two big ideas here, two big concept ideas that are being investigated. A European-centered concept is this Einstein telescope. The idea, it's a 10-kilometer underground sort of LIGO, Virgo, Kagra-like concept. At the bottom, you can see the time scale. It could be that this is something that could be ready for operation around the same time frame as LISA. Similar time frame for Cosmic Explorer, which is a US-led concept. It would be a future for LIGO. They're thinking bigger, a little bit bigger, 40 kilometers, but I think overall there's similar sensitivities. So these are being investigated, sites are being looked at. Reality of the project is being considered. If you can do that, then you can see a lot farther of some of the same kinds of things that you can see. So on the right, you can see a kind of diagram of what this whole space of possible observatories could see. The blue curve, so the white and the yellow dots are estimated populations of binary black holes and neutron stars, respectively. So the binary black holes on the right. The blue curve there is kind of representing where we think we are in terms of the current sensitivity of today's instruments. And the purple and green curves are where these Einstein telescope and cosmic explorer could get you to. So, which, if this kind of model of the population is right, is essentially all of that population. For the neutron stars, we're really barely able to see any of the population so far. But you could see potentially almost all the population if you have these new instruments. So it's a dramatic change in what we're able to understand about this population. You can also potentially see some other kinds of systems that we're not really seeing yet, but I'm going to keep going. All right, this is sort of my second to last slide, but we're going to be on it for a while. So what are the challenges associated with these future observations, other than being able to actually speak? That's apparently one. And I mentioned a few. These are obviously not the only things, but challenges and opportunities sometimes look the same thing. So you got a lot more sources, a lot more kinds of sources, right? So now we've been seeing signals from the two on the top right there. I mentioned a few other cases here, but there's a whole range of possible things that we could be seeing in the signals of these systems. And I'm just going to let you look at the pictures and not try to explain them all, both because I have no time and because I have no voice. So next category, there are more events, right? So as we sort of saw in the 3G systems, right? So, and this is a plot showing you purely a realization of a population of binary black holes like the ground-based observatories see, and binary neutron stars. And you can see, and there's no noise in here. It's all signal. And in fact, if you dig deep enough, the point being here, if you dig deep enough, there's signal there all the time, and you're just seeing more. You're seeing all of those neutron star binaries and all of those black hole binaries in the universe. Well, there's quite a few more of them. So for today's observatories, there would be less than one. You would expect less than one in this period of 10,000 seconds here, right? But here you have just large numbers, and so some of them, like the binary black holes, are better separated, but really they're kind of always there together. And that gives you challenges because you have to manage to do the analysis where you get all of those at once. And we already have that kind of challenge to some degree with LISA, because those galactic binaries are so numerous that they're all piling up on top of each other. And I didn't point it out too much before, but where this arrow is pointing in the plot, there's a part of the sensitivity region where it doesn't matter really how sensitive the instrument is, because all of those binaries are being piled up on top of each other. We won't be able to distinguish them, and they will be their own confusion, their own source of noise, right? Or their own stochastic signal that we can look for. And there are others. So higher SNRs is great. And it means that we can see more physics, but it also means we have to model more physics, and more physics is interesting and relevant to the data analysis. So one example is things like the eccentricity of the binary. We have very difficult to get any information about eccentricity with the current observations for most systems. But with LISA, even for the massive black holes, this plot, the dark blue curve there is showing for a system at a redshift of 1. So the masses are on the bottom axis, and eccentricity is the left side axis. Maybe you can't see it very well, but it goes from like 10 to the 4 to 10 to the 8 solar masses. It's a wide range. So for 10 to the 4-ish solar masses, you can measure with LISA at a redshift of 1 an eccentricity of a part in 1,000, right? If you go even lower in mass, where you're sensitive to the binaries that we can see also with the ground-based observatories, which I somehow skipped over, then you can measure the eccentricities even if they're much smaller. So there's a lot more details of the signals and more information in the details, but it also means we have to model them. And so there's a lot of things right now in our waveform approximations that, well, they're not perfect, right? So we need to make them much more perfect if we want to take full advantage of all the things we can do with them. There's also more astrophysics that can be developed. And hopefully I have clicked this and it will jump to the next slide. All right, well, there's more astrophysics that's relevant too. So is for those systems where we're making really high SNR observations. There we go. Um, things, so the top plus, so for the ground-based observatories, if we become more sensitive, we can see more of the physics of the interaction, and things like for the neutron stars, we can see when the interaction between the neutron stars starts to be more important. And then there's going to be a lot more astrophysical details in those signals than what we're dealing with now, where we can just kind of treat everything as a point particle. Similarly, for these binaries in the galaxy, they can actually be interacting, touching each other in a sense. And the flow of gas from one star to the other can have the effect that it actually stops the chirp, causes the chirp to change direction. It can start chirping backwards. There's a tidal effects from the neutron stars. Tidal effects from these stars potentially could be something you're interested in. There's a large number of environmental effects that could potentially affect some of the binaries. There's gravitational lensing, both the weak lensing and strong lensing, the acceleration of the sources, a lot of things. The more finely you measure them, the more chance you have of some of these effects being observable and interesting, and also hard to model and more work to do for the data analysis. I mentioned the stochastic infusion noise. It's one of the most exciting targets of gravitational wave astronomy, if it's possible, would be to observe a cosmological gravitational wave background from the inflationary epoch of the universe. We can't see that electromagnetically because in the early history of the universe, it was all this hot mess that was brightly glowing and is completely opaque. You can't see through it electromagnetically. That's why what we see in the microwave background is we see the remnants of the point where that period stopped, right? But with gravitational waves, you can penetrate that, right, and see earlier. Okay, running out of time. Another, so I just click and then hope that it's going to change. I'll keep talking. The next category here is a challenge that we have, these unique new instruments. And there's both parts of that are interesting. They are new. Oh, okay, that's too far. If I do it by hand, is it faster? All right. Then, so because our instruments are new, they work differently, right? Some of that changes some of the aspects of how you have to work with the data. One of the things that was shown in an earlier talk by Tito was that you can sort of calibrate the detections. Like if you can really assume that everything is Gaussian noise, right? It's easy to make inferences about whether you should really believe that you detected something. If it's possible that your instrument does some weird non-Gaussian things, then your ability to believe that depends on what your assumptions about the instrument are. So they do a lot of work with these, calibrating the false alarm rates, and they do that by comparing the data from the two instruments. That's how I understand it works. Lisa, we only have one instrument, so we can't do exactly that. That's another kind of challenge. We have to figure out how we're handling that kind of situation. There's also a lot of different ranges of different possibilities that have been considered for the future, right? We could not be doing these interferometers at all. We could have atom interferometry based instruments, where there's instruments being built on the moon, or a whole bunch of different concepts that are out there. All right. And lastly, there's a whole bunch of new multi-messenger types of concepts. And I mentioned a few of those as we came along. Let me not try to go into too much detail. I want to point at this one, though, on the in the bottom corner there, which I kind of skipped over earlier with Lisa. We can see the same systems that LIGO sees, of these stellar scale sort of black hole mergers, but we see them before, and by making joint observations and joint analysis of the data, then we can learn even more than we could otherwise. So I have just one last slide here, which I will leave with you. I don't have anything to say about it, but you can participate in this, and I tried to find links for a number of these different projects. I'm not sure if they're the right links, but they're there for you to try. A lot of science collaboration is working on the future. Sorry for.
Thank you, John. Thank you for going through, even with your voice fading. don't worry. Apparently, online everything was clear. So the mystery of all of this. There's a few questions online. Okay. So there is a first question online by Luis Cardenas, who asks, when will we reach a distance of 14,000 megaparsecs with LISA, 2035 or after?
I don't know. The 14,000 megaparsecs. So 14 gigaparsecs. That's about a redshift of 3 or something, I think. I don't know, 2 or 3. So as soon as Lisa starts operating, it's going to be at the sensitivity. It's not going to be improving over time like the history of the ground-based observers, because you can't go there and mess with it. It just either works or it doesn't. I mean, that's not completely. There can be some adjustments, but it will work. It will work at its best or near its best from the start, and probably usually you expect space observatories to degrade over time rather than to improve.
Also, if I'm correct, the duration of the mission is, I think the nominal duration is 4 years.
Yeah, the other details, not 2035, because that's the year of the launch. It takes it a year and a half to get there where it needs to go. So it'll be, hopefully sometime in 2036 when we get the first data.
Okay. Thank you. There is another question by Ida Khan. I think it's about Cosmic Explorer. With a 40-kilometer arm length, wouldn't the curvature of Earth play a disruptive role in the interference of the Cosmic Explorer?
I am not an expert on that, but yes, the curvature there is very important for those kind of things.
I think this is taken into account.
Yeah, sure. They're aware of that. Yeah.
Hopefully. Okay. Okay, there is one last question online by Angela Mogin. How can DWDs make reverse chirps, aren't chirp signal of the final merger?
What was the last part?
Aren't chirp signal, aren't chirp signal of the final merger.
Right. So the white dwarfs are not the same as black holes, right? And they're definitely not going to have anything like a black hole merger. It could be that some of them, so I mean, they start out not touching each other. We call them detached binaries. But as they get closer together, they're not point particles. They're like stars. They're very, very compact stars. But eventually they effectively touch, right? And once they touch, then there's a number of scenarios. They could blow up, and this could be this type 1A supernovas, or they could somehow merge, or but in some cases, they could start just transferring mass in a kind of steady way from one to the other. And in that situation, it can be that that they kind of move, that you have a transfer of angular momentum that causes them to kind of slow down in their orbit. But because it's not the same anymore, one star is sort of sending part of its stuff over to the other one. And the chirp that we all know and love from the neutron stars and the black holes, like that is based on the assumption that gravity itself is the only thing that matters. The interesting part of some of these other parts of the whole parameter space of binaries is that sometimes other stuff matters too.
Thank you. One question appeared online by an anonymous person. The data release for LISA is going to be first L1, then L0. How long would an independent researcher have to wait before they have access? Maybe you can define what L1 and L0 are in this context.
Yeah, so I don't know that we have an exact schedule for how the data gets released, but we do. There's some pictures of that. So LISA has a whole hierarchy of different levels of data that depends on how much processing has the numbers sort of depend on how much processing. So the data we get directly on Earth from the satellites won't be immediately useful. That's called the L0 data. Not all of the L0 data will necessarily be released. Some of it is just technical information. But the ones that get used for the downstream processing will be released along with the big data releases. So the L1 data has been, basically treated and has a gravitational wave signal component to it, and it's a time delay interferometry channels is what we expect the L1 data to be. It will have removed some key sources of noise in the raw measurements, because the raw measurements themselves are not like directly recognizable as useful. So you have to actually form some linear combinations of them, which cancel out parts of the instrument noise. So that are the technical part of the whole entire design of LISA. But so that's L1, and then there's L2, which is data that's been analyzed farther, and we tried to find, there'll be burst alert type of events, low latency data that comes out on a short time scale, and there'll also be like the analysis of all the signals that we think is in there will come out in some kind of a global form, and then that'll be processed into catalog forms of some kind. That's the L3 type of data product, which is much more directly accessible for a typical astronomer.
A good exercise for all of you is to relate the different levels that John explains about LISA with what we do on the GWOSC website. Right? I trust you do that. I know the answers. Okay, there's no more question online. Is there any question in the room? Yes.
How do rotating neutron stars produce gravitational waves? I thought it was spherically symmetric, kind of, so they don't.
So if you produce, so there was on the slides, I didn't talk about it, but one of the possible sources, if you can dig deep enough with the ground-based observatories, is to observe a rotating neutron star. If the neutron star is really symmetrical, then it's not going to produce a gravitational wave. But the neutron stars, we don't, of course, understand the nuclear matter all that well, but the crust level of a neutron star could have a kind of a solid layer that could support some structure. And so it's possible that we have these neutron star quakes. You do see these kind of events sometimes in the neutron, the pulsar data that maybe suggested this is a thing that happens, that the neutron stars can sometimes have some changes in structure, right? Which could produce, basically they could have structure to them that is producing gravitational waves, right? Capable of producing gravitation.
What's the time frame for the Chinese projects, and is there a possibility that there would be at least two space interferometers at the same time in the sky?
The time frame for which project?
I mean, the Tianjin collaboration. That you mentioned Chinese space missions.
Oh, sorry.
So
I can't say I really know anything about that. I don't know how much anybody in the world actually knows anything about that, but I know that they talk like they're aiming for timeframes that are similar to that of LISA. Whether there could be one or two is also one of the things that I don't know.
Is the international?
I'm afraid I will say something stupid there, but I'm sure I will say something. Probably saying that.
Is the international community getting ready for having two interferometers in space at the same time?
Sorry, is it possible for having them at the same time? Is that what you're saying? Are we getting ready? So I would say we're thinking about the opportunity of that. I don't think we are concretely develop anything yet to sort of handle that. But I would love to be having enough information to be able to work on that in a confident way. It's very interesting.
Thank you. Any question online? There's no more questions.